already know about it. Okay. She is short, and so
I'm short. So
yeah, I think she's exploring.
Yeah. Okay. So I'm going to. Okay. Well, everybody got really quiet, so I guess we can start. So, welcome to CASI. Okay. My name is Tom DeGrand. I'm the local organizer. I'm responsible for infrastructure, which means I get somebody else to do things. We have Ruben over here, who is one of the two directors. After that, they put together a really nice program. I'm looking forward to CASI. But before we get started, there are some administrative details. Okay. So some of you didn't pick up registration material. We'll bring down the box of cards and registration material and things like that at the top break and pick stuff up then. Okay. Coffee will be on this side of the hall over here, just out there on the area that turns back. Bathrooms go over that way. Let's see, local people. So me, Tom DeGrand, Oliver DeWolf, local faculty member, is he in? Yes? No? Okay. Emily Barber, who was the woman we saw running around yesterday. She's the one who knows everything. Okay. Graduate students, Will Jay, Dan Hackett, Oscar Hendrickson, and Van Rowe. Okay, they're all over there. So if you want something and you're afraid to ask somebody old, you get them to do it for you. Okay. Our AV guy is Skip, and I don't know your last name, he's back there. If you have issues trying to read videos and things like that, send an email to cassie@colorado.edu and we'll do our best to fix it. Okay. Let's see. Second thing, student seminar. So, there's the okay. Good. Even other faculty members. Student seminar. People, you guys are all in this here and wanting to talk to each other. Okay. So I need to. Now we have 2 rules. So I need 2 volunteers to organize things. Okay. Talk about yourself, organize yourself for the next day or so, and tell me. And what I will do is our web bar and something to right access. Up until a few years ago, these were very elaborate things. We're talking for 20 minutes or half an hour, and these got tremendous time. Okay? You shouldn't do that. Okay? So keep them short. Okay? The typical student talk is, my name is Tom Grant. I'm just read my paper. I am a graduate student at MIT. My advisor is Carl. Thank you. Okay. But don't do anything more than that. The organizers have to do that. Okay. There's an opening reception tonight after dinner. It's on the top floor of the Hamlock Tower. There are 2 towers in the complex. There's the Villa Tower over there, the Hamlock Tower, which is over close to it. Go in at the base. The elevator is to the top floor. That's where it will be, and we will have some local person there saying the elevator is to the top floor. That's fun. You need your name tag. You absolutely need your name tag. You need your name tag for the name tag. Okay. The reception tonight took out over at Forest Peak in 2 weeks, and the banquet the last week. And we finished the meeting at the university has our alcohol rules. Okay. Coloradans are like every banquet we see events. And there is an organization at the university which is devoted to the course of so you need your name. There'll be a group photo, 4 morning coffee breaks, everybody outside, back here, pictures. There's a public lecture by Leon on the 28th of June, I hope. Okay. Okay. Let's hope for the best. We want to do a procedure. Okay. We have activities to do a procedure. In order to do a procedure, the lecturers have to write up their lecture. In order for the lecturers to write up their lecture, you have to tell them over and over and over again how important it would be to have nice, big coffee on a job, but not other topics that we have to do let's see. T-shirt, Oliver. Okay.
This is a vintage Tassie 99.
I passed 99 T-shirt. It's long gone. I carry the ones that look nasty. T-shirts are, there are a lot of nasty. Okay. T-shirts are a student design. From design. As far as I know, there's only one Tassie that's not covered. I'm not sure about that. Self-organized. Last year, four of them on last year, we Friday on the last day. Okay, that was a screening test. Okay, I'm allowed to say it's not a screening test. It's not a screening test. You are not screening. So last week, and graduates, they want to, but my part of the thing is, come up with a design. I will give you a large check and a list of sizes for the lecture. Okay.
For Thursday morning, and then I'll leave on Friday.
Let's see, what else?
I'm giving these same lectures in Mainz.
Working on parts, I'll announce details on Thursday. Let's see, last night we uncovered a lot of typos in name tags and affiliation and emails. So you should go into the folder
They have apartments for visitors and guys went together.
Is everything good? If you don't have your registration stuff, we'll bring it down. Take a look at
Yeah,
it.
they have a ton of money.
You don't need it.
Yeah, that's right.
We'll reprint, get everything reprinted. From the next one. The other one. Okay, that's the you don't care what happens after 2000. You aren't ask a lot of questions. Get plenty of time. Figure out first. Let's see. Ruben, you want to say something, I guess. Okay.
Okay. Okay, so my name's Sally Dawson. I'm a theorist at Brookhaven Lab. I've worked my whole career pretty much on the Higgs boson. This is the fourth time I've lectured at Tassie, and I have to say it's one of my favorite things to do in the whole world to come here. But you'll be happy to know these are new lectures, not the old ones. So to me, what really makes TASI great is if you ask lots and lots of questions. You know, if you're wondering about something, probably somebody else is wondering about it too. So you should speak up, stop the lecturers from blathering on. You know, you put a quarter and I can talk forever about electroweak symmetry breaking. So you should stop me. Stop everybody. The lecturers are around at lunch, you know, the coffee breaks. We're friendly, you know, so come talk to us. All right. So I put some stuff on the Twiki, if you look at it. And what I put on the Twiki to start with was Heather Logan's lectures from 2013. So those were the first TASI lectures after the Higgs was discovered. And Heather and I think a lot alike. So if you look at her lecture notes, you'll find that I think they're very, very useful. The other thing I put on the Twiki were Tillman Plen's notes on LHC physics, which maybe some of you have seen. Tillman was a student here 20 years ago and describes it as one of the formative experiences of his life. So it's kind of nice to come back to his lecture notes. And you'll see, I think, if you look at them, that there'll be a lot of overlap with what I say and probably with what Matt Schwartz says after me. I also put on the Twiki what I call backup. And that's because I'm going to use the Blackboard, but sometimes you want to show slides and things. So I put plots in the backup. So sometimes I'll refer to the backup for plots that you might actually want to look at. Okay, so I'm going to talk about electroweak symmetry breaking and the Higgs. And the way I'm going to talk about it is that we know that the standard model is a pretty good standard model. It works. We haven't seen anything that makes us think that it's not a good theory. So I'm going to talk about the standard model in the context of it being a really great effective field theory. So as I present the standard model and electroweak symmetry breaking, I'm also going to talk about effective field theories and how they play into this whole idea of electroweak symmetry breaking. Okay, so I mentioned references. Everything I know about electroweak symmetry breaking is actually contained in a book by Chris Quigg on gauge theory. So if you know that book, it's a great book. My conventions are the same as Chris's book, and they're also the same as the Higgs Hunter's Guide. And you'll see that that particular set of conventions is a little bit old-fashioned, but I thought if I changed it, I'd screw things up. So it's Higgs Hunter's Guide conventions everywhere. Do we have white chalk? Yes. Okay, I'm a boring person. I like white chalk. Okay, so please tell me if you can't, especially in the back, if you can't see the boards, let me know, because I'm short and can't fill up too much of the board. So I'm going to start by talking about, my plan is to work this way and see how it works. The Abelian Higgs model. So the question of electroweak symmetry breaking, of course, is why is the W mass not zero? How does the W boson get its mass? So if you start with a U1 theory with a gauge field, okay. Can you read it in the back, that writing? Is that big enough? Oh, yeah. Okay, good. You mean I could write smaller? All right. So the Lagrangian for this, minus a quarter, F mu nu, where F mu nu is, is this thing on? Yeah. F mu nu is d nu a mu minus d mu a nu. Okay, so there's QED, right? It's just a photon here. But this is invariant under the transformation a mu x goes to. Okay, so I can subtract, obviously, any field here, and the Lagrangian is invariant. Okay, so this is the U1 gauge invariance. So, aha, we know why the photon is massless, because if I try to add a mass term, okay, so a mass term, okay, I can't add a mass term. It violates the U1 gauge invariance. Okay, so that's great. We know why the photon is massless. So that's the one that doesn't work. All right, continuing. Okay.
You can also pull this one down.
Yeah, but then they can't see my brilliant words there. I got a theory here. We'll see how it works. I might need a little practice at this. Okay, so to my very simple model here, I'm just going to add a scalar field. So if I add a complex scalar field, scalar phi with charge minus E. Okay, so my convention here is that E is positive. E, great. Okay? And that's not the convention that everybody uses. Sometimes people use the convention that E is negative, and it works its way into the covariant derivatives. So this is Quigg's convention. E is positive. Okay, so I'm going to add a complex scalar field here. So now my Lagrangian, minus a quarter F mu nu F. What's that? Okay. Plus d mu phi squared minus v of phi. Okay, so here we have the covariant derivative for my scalar, d mu minus I e a mu. And the scalar potential is mu squared pi squared plus lambda. Okay, so here we go. This is the most general potential I can write with the scalar field phi. It's invariant under my gauge transformation here if you want to play with it. Okay, by convention, lambda is always chosen to be positive. Because if I chose lambda to be negative, the potential would be upside down and there would be no state of minimum energy. So lambda is chosen to be positive. Yeah. Oh, this is fun. Okay. So if I tried to add a cubic term to that potential, of course, I couldn't do it, right? It wouldn't be invariant. So mu squared greater than 0, we have the classic case, the potential v of phi just looks like this. So nothing's very interesting is happening. So the minimum is at phi equals 0. This is QED, right? QED with the mass of the photon equals 0, and the mass of the scalar equals mu. Nothing interesting. That's QED. But who told me the sign of mu squared? What if mu squared were negative? So if mu squared were less than 0, I've got my famous Coke bottle potential here like this. Here's v of phi, and here's phi. So now the state of minimum energy is not at 0, but it's over here. So this 2 lambda, and we'll just define this to be v over the square root of 2. Okay? This is convention, the square root of 2. Older works tended not to have this, but modern works have v over square root of 2. So here we go. So mu squared is negative, so this is positive. The state of minimum energy is here, mu squared less than 0. And this is actually was one of the original motivations for some of the grand unified SUSY models, because you had these grand unified models where everything was unified at the gut scale, and you could actually get mu squared less than 0 by evolving your parameters from the gut scale down to the weak scale. So that was kind of a nice feature of the early grand unified models. And in fact, in order to get mu squared less than 0 in the grand unified models, you needed a heavy top quark. So Michael Dine actually predicted the top quark mass and got it about right in 1994 or something, way before we discovered it. Okay. So now I'm going to rewrite my scalar field, phi equal 1 over the square root of 2 e to the I chi over v times v plus h. Okay. So h is a field that has its minimum at 0 because I've shifted it here, and chi is a physical degree of freedom. We call it a Goldstone boson. So if I just go back to my Lagrangian and just do simple algebra and write it all out, I get something very interesting. minus a quarter F mu nu, F mu nu, minus E V A mu d mu chi plus E squared V squared over 2 A mu plus a half d mu h plus 2 mu squared h squared plus a half d mu chi plus some stuff I don't want to write down. Okay, so this seems really simple, but something profound has happened now by having this funny potential with the minimum there. Because here we go, okay? So our gauge field now has a mass, EV. We've generated mass for it. We have a physical particle, H, right? It's got a kinetic energy term, so it's physical. It's got a mass here, minus mu squared h squared. Remember, mu squared is negative. And we've got something else left over. We've got this field chi, which has a kinetic energy term here. So it's a physical field. And this thing is the thing we call the Goldstone boson. So for those of you in the room who say that this is just trickery, right? I just made this potential and then I played around with it. There's a physical prediction. It's a scalar field H. That if this thing is real, you got to see this physical field H in order to explain this mass A. Okay. To a lot of us, this term looks kind of funky, right? It's a term which mixes the gauge field and the Goldstone boson. Okay. So, yes? Where? Up there?
Near the top left, should it be 5 each of that?
Oh, did I get the square root of 2?
Because of the dimension. It shouldn't be in the exponent.
Yeah, it's my typing. It's not in the exponent. Sorry. It's just sloppy writing up there, yes. It is not. Let me write it more carefully. Yes. Yeah. There we go. Yeah. Chi over V. Yeah. Thank you. Okay. So that mixed term up there looks funky, and what we're going to do is get rid of it just by a gauge transformation. So we'll just redefine A prime mu equals A mu minus 1 over E V d mu chi. Okay. And we'll define phi prime equals e to the minus I chi over V phi equals V plus H over the square root of 2. So I would have caught that when I got down here. Okay, so this is just a gauge transformation on the gauge field, and all it does is get rid of that funky term which mixes A mu and D mu chi. Okay? So the chi field now doesn't have any interactions. Okay? So sometimes people say that the chi field was eaten, but all that means is that it's been absorbed in your gauge choice to make A mu have a mass. So now remember, a photon, it's got 2 degrees of freedom, right? It's got transverse polarizations, plus and minus. A massive gauge field has 3 degrees of freedom. So it's got a longitudinal degree of freedom on top of the transverse degrees of freedom. So as you count degrees of freedom, the degree of freedom from this chi field just turns into the longitudinal component of the massive gauge field. So this particular gauge is called the unitary gauge. It's a nice gauge in the sense that it doesn't have this chi field, which we needed to sort of explain the electroweak symmetry breaking. It's a bad gauge in that the A propagator has bad high energy behavior. So del mu nu of k equals minus I k squared minus ma squared. That's fine. G mu nu minus k nu over ma squared. So if I try to use the unitary gauge where I don't have to worry about these Goldstone bosons, then I got to worry about the fact that the propagator grows at high energy. So it's not a very convenient gauge. So the so-called RC gauges are more convenient. So for example, there's a parameter chi in them, or zeta ma squared. So the chi field, if zeta is 0, you don't have the interactions. If zeta is 1, the chi field just has the mass of the corresponding gauge field. So Feynman gauge, chi equals 1, corresponds to Feynman gauge. Feynman gauge. So if I take this parameter equal 1, I've got the chi field in my spectrum, so I got to calculate with it, and it's Feynman gauge for the gauge field. So that's a very nice gauge. I will be talking as I go through these lectures about these Goldstone bosons a lot, and sometimes using unitary gauge because they have very nice properties. So that's how electroweak symmetry breaking works in this trivial example. So now it's very easy to go ahead and do it in the standard model, which I'm going to sketch. And if you need to, or if you're inclined to work out the details of the standard model, I highly recommend Heather's notes. Okay, so this is very simple, and it's super duper easy to construct the standard model now. That's the one that, all right. Now I'm going to have to erase it, okay. What's that? Oh, I think we played with it earlier and decided no. We were checking it out earlier. We have a fit. Doesn't matter. So. All right. So let me encourage you, at the coffee break, at lunch or something, just to work out the math here, because it's not very complicated, but I think it's useful to get a feel for how this stuff goes. So the standard model now is an SU2 cross U1 gauge theory. So we're going to do exactly the same thing. We're going to add a complex doublet. Complex Higgs doublet phi, where, okay, phi equals 1 over the square root of 2, phi 1 plus I phi 2, phi 3 plus I phi 4. Okay, so then I'll just write down the most general renormalizable potential, just like I did before. So the scalar potential is going to be mu squared phi dagger phi plus lambda phi dagger phi squared. Okay. So just like before, mu squared. We're going to take mu squared negative, and we're going to get this same cookie cutter potential here that it's going to look just like this. Right. So we're free to choose the direction in this SU2 space where we're going to give the VEV here. So by convention, we always choose that the VEV of phi equals 1 over square root of 2, 0 V. That's just a convention. You got to pick it somewhere that defines our SU2 space. Okay? And this is, of course, written right here in unitary gauge. So just because I'm lazy, I didn't write it with the Goldstone bosons. I will do so later, writing the Goldstone bosons here. Okay. So now we can see the I guess this works okay. We can see the miracle of the standard model. We'll write the scalar potential, d mu phi dagger, d mu phi minus v of phi, where d mu is now SU2 cross U1 invariant, so it's d mu plus I g over 2 sigma a w mu a plus I g prime over 2 y b mu. Okay, so b mu are the U1 gauge bosons, so these are just like the A's that I had before. W's are the SU2 gauge bosons, and it's terrible notation, but everybody's used it for centuries. So these aren't the W plus or minus gauge bosons that we've seen. These are 3, A equals 1 to 3. These are the 3 SU2 gauge bosons. What can I say? It's a pity. And these are, of course, the sigma matrices. The one thing to note here is I have a plus sign here. Where's Matt? I'm willing to bet that Matt has a minus sign. It's simply, right, in your covariant derivative? It's a convention. So it's a convention. So my words of wisdom to you guys is if you pick Feynman rules out of a book here and a book there, check how they define their covariant derivatives. Because if they define them differently, then there's relative minus signs. Having made that mistake many times in my life. So this is my convention. Okay. So you can see that we're now going to generate masses for the W's and Z's. Okay. So sigma W operating on phi, going over here, hitting the V, you're going to get some mass terms. Okay. Let's see here. And let me just write out how the masses come. Okay, so from these guys, you get a half from each of the covariant derivatives, and you get a 1 over square root of 2 from each of these guys, so you get an eighth. So this thing goes to an eighth. So here's the Higgs with just the V. G W mu A sigma A plus G prime B mu G W B mu sigma B plus G prime B mu. Okay, 0 V. So you guys got a 2 by 2 matrix here to diagonalize. I'm sure you can all do it, but I would encourage you to do it. Okay, so you get terms here with the B squareds, and you get terms with various combinations here from the sigma fields. So you end, and nobody asked me what happened to my parameter y. You guys are asleep.
What happened to your parameter y?
Good. Why did I set it equal to 1? Right? I set it equal to 1. And the reason I set it equal to 1 is that y is what's called the hypercharge. Okay, so the y that comes in here is this thing which would be the hypercharge of phi. So let me see. I wrote it down here because I'm trying to get everything right. Let's see. Let me write it down here. So we have T3 plus y over 2 operating on, say, the vev of phi equals 0. And this T3 plus y is Q electromagnetic operating on phi. Okay. So the electromagnetic charge here is T3 of the field. So that's normalized so that it's plus 1 for the numerator and minus 1 for the denominator of an SU2 field. And this is an old relationship Q equals T3 plus Y over 2. Okay, so for the doublet, Y is 1. Yeah, and that's why I set it equal to 1 here. I didn't just forget it being sloppy. I set it equal to 1. And you will see more of this relationship when I start talking about fermions. But this is an important relationship, right? Because this says that this VEV of phi doesn't break electric charge, right? So it's structured so the electric charge is unbroken, which is a very fine thing. Why do you do it?
Yeah, somehow we've made a choice somewhere.
Yeah, we've made a choice, and we made the choice when we picked this, okay? Because the SU2 field now plus, okay? So we've made the choice that this is my SU2 field with the charged guy up here and the neutral guy down here. So yes, we've made this choice when we fixed it here. Yeah. So this is important because when I come to put in fermions, this is going to tell me how the fermions couple to the gauge fields. And that's going to give me the fermion couplings to the Z. Okay. All right. So this guy, we can write it out. I'll write it right here. Hopefully you can read this. So it's V squared from these two guys over 8 G squared W mu 1 squared plus W mu 2 squared plus G W. Okay. I'm trying to get all my factors right here. There's nothing worse than having wrong factors. Okay, so all I've done here is multiplied sigma matrices to get these guys. Okay, so this combination of fields, so there's a piece from the U1 and a piece from the SU2. This is going to turn out to be the Z. The orthogonal combination will be the photon. And these guys here are the charged W bosons. So this combination is W plus and W minus. Yes? Yeah. Thank you. Yes, absolutely. And the reason that was yeah. I'd probably make lots of mistakes. You know, even when you proofread your notes 100 times. Yeah. And that's an important comment, though, because V goes to 0, the masses go to 0, which is the whole point of the spontaneous symmetry breaking, is that the masses are proportional to this thing, V. Okay. All right. So now we can have fun diagonalizing 2 by 2 matrices. And I decided not to do that here because I'm pretty sure you all know how to do it. But if you haven't done it, you should do it. Did I say that enough times?
Sorry, are we getting the back up right?
Yeah, that's right.
Oh, yeah.
Yeah, that's right. Absolutely. And in fact, I'll write down the equation and you'll see that it's right. Because you thought the mass was G squared V squared over 4. That's why you're asking the question, right? Yes. Yep. So let me put in that step to answer the question. Okay. So we've got the charged gauge bosons and the neutral gauge bosons. So W mu plus minus. So these are the real guys, the physical guys. They're equal to 1 over the square root of 2. W mu 1 minus or plus W mu 2. Okay. So one combination, I think I forgot an I here. Yes. So one combination gives you the plus W boson, or one gives you the minus W boson. So you can ask, how do you know which is which? Okay. Good question. And you'll know which is which when I couple them to fermions and you see charge conservation. That's the easiest way. So you can actually see from putting this into that, MW equals GV over 2, which is a familiar relationship. Okay? And MZ is equal to the square root of G squared plus G prime squared V over 2. Okay? And one typically defines... Do I need what? Yeah, you could get it from that relationship too. But I kind of, yeah, you can get it from that relationship. It's just easier with footnotes. Okay, so we typically define cos theta w equals g over the square root of g squared plus g prime squared. Okay, so we got the w mass, we got the z mass, and we've got a relation between them. We have rho equals 1 equals mw squared over mz squared cos squared theta w. Okay. So cosine theta w is going to come in the couplings of the z to fermion. So it's a physical thing that I can measure. So when I measure things like, say, Drell-Yan, z goes to mu plus, mu minus, that coupling is sensitive to cosine theta. So I can measure it. I can measure the w mass. I can measure the z mass. And I see that experimentally, rho is very, very close to 1. The errors on rho being away from 1 are very small. But this actually tells us something really important about electroweak symmetry breaking. Because where did rho equals 1 come from? It came from way back here when I'm writing down the masses from the covariant derivatives here, right? So what if I tried to construct a model where phi was not a doublet? Because who told me that phi had to be a doublet? I just put that in because SU2, it's easy, you know. It's kind of the easiest thing I could write down. So what if I said, well, I don't know, maybe phi should be a triplet, okay, an SU2 triplet. That was popular at one point. No particular reason not to have a triplet, okay. So suppose you put in, what shall I call it? I'll call it sigma equals eta plus v prime plus eta 0, eta minus. So I'll put in a scalar field that's a triplet. And I'll work through the same algebra, right? I'll couple it to the gauge field. I'll find, because I put in spontaneous symmetry breaking, I'll find the masses and so forth. And what happens? What happens is that mw squared is g squared v squared over 2 from a doublet plus g squared, let's see, let me get my algebra right, v prime squared, okay? Whereas mz, the z gets no mass from the coupling to a triplet because you cannot make a gauge invariant SU2 coupling. So if I try to add a triplet, I get a contribution to the w mass, but none to the z mass. So then I would break this relationship rho equals 1, right? I would have rho equals 1 plus 4 v prime squared over v squared if I had a doublet and a triplet. So, okay, triplets don't work because they ruin an experimentally measured quantity unless you make this v prime super duper small. A triplet with an epsilon tensor. Yeah. For these guys? Triplet scalar with some epsilons. Yeah. Oh, yeah. There are lots of ways to do it. Yeah. Right. Yeah, I'm not going to work it out, but I could. Yeah. Right. My point is you can't add different representations. Yeah. I'll work that out, actually, with the Goldstone bosons later on. Okay. So, all right. Okay. If you add more and more Higgses? Well, I can add as many doublets as I want, right? The more doublets I add, it doesn't do anything except put some angles in here. So doublets are great. I can add as many as I want and still get rho equal 1. I can add as many singlets as I want and still get rho equal 1. But other than that, it doesn't work. You don't get this relationship. So then you have to play around to make things artificially small. Okay. So, okay. So now, having introduced this simple model, now we can start to play around with what happens with the Higgs boson in this kind of model. So, my plan for the next few lectures is that today I'm going to work out some of the Higgs couplings, probably finish them this afternoon, so then we can talk about Higgs production and Higgs decay. And then I'm going to talk about effective field theories and how they get into this whole picture of things and what they can tell us about physics. And then in my last lecture, I'm going to work out in detail how you measure the Higgs width by looking at z-pairs, which is a good example of the physics that comes into electroweak symmetry breaking, of how it works and doesn't work. Okay, so we have over here the kinetic energy term for the scalars, d mu phi dagger. From this, we can always find the Higgs couplings, because we know that we started out over here with the doublet phi, and then we shifted it just like in our simple model. So we can write phi is equal to E, geez, I'm too short, I omega dot sigma over 2V times 0. Okay, so just like in our model where we only had one scalar, where we had e to the I chi, we can have the Goldstone bosons up here, except now these are omegas, so there are 3 of them, so there are 3 Goldstone bosons. So this is just like the chi field in the simple case. So the point is that you always get the combination V plus H. That's what enters in to all of your kinetic energy terms. Okay? So if I go, where are we here? The mass terms, the phi's, instead of putting in just V, I could put in V plus H here, because that's where I started from with my phi field. So I can have d mu phi dagger d mu phi. Keeping the Higgs field is going to give a half g squared over 2 W mu plus W mu minus. These are now the physical W's times V plus H squared. So this is from the covariant derivative piece in this guy. Plus G squared over 4 cosine theta W squared Z mu V plus H squared. So we get the coupling of the Higgs to the gauge bosons. Okay, so the coupling of the Higgs to the gauge bosons, here's we'll call Higgs W plus W minus. It's I, G, and W, G mu nu equals 2I. Okay. So depending on whether you hold V fixed or G fixed, you get MW or MW squared. So in the plots that CMS makes, where they plot the Higgs couplings versus the mass, in order to get a linear mass, they keep the coupling fixed. So the couplings to the gauge bosons are just proportional to the mass. And similarly over here, you get a cosine theta in the denominator. So if I calculate this decay width here, it's pretty simple, of course. It's I G squared V over 2 epsilon plus mu of W plus epsilon minus, let's see, epsilon mu of W plus epsilon nu of W minus G mu nu. Okay, we know that the sum of the polarizations of the epsilon tensors are some, epsilon plus epsilon minus of, say, let's both call PW plus equals minus G mu nu plus P mu plus P nu plus over MW squared. So something interesting happens here when we calculate this decay width and just sum over the polarizations here, because I'll cover it up. Well, that's probably not a good idea. I'll go over. I don't want to cover that one up. Okay, so I'm calculating the decay width of H to W plus W minus, so the amplitude squared, summing over those polarizations, G squared MH to the fourth over 4MW squared, 1 minus 4 MW squared over. Okay, so then I can find the decay width. It's just gamma H to WW. Let me write it down, then we'll talk about it. It's equal to 1 over 16 pi MH beta times this amplitude squared, where beta is okay. So the first thing you should notice here before you tell me I've swindled you is that this grows with MH cubed, the decay of a Higgs boson to W pairs. Okay, so the Higgs, as its mass gets heavy, gets very, very wide. Okay, MH cubed. Okay. And why does it grow like MH cubed? It's because we're seeing the longitudinal couplings of the Higgs. So this growth here, this first term, this one, is coming entirely from the couplings to the longitudinal gauge bosons. So this is telling us something about the underlying symmetry, this growth with the mass. Okay. Yeah. Yeah, now you're getting to the swindle. He's waking up to get the swindle, right? Yeah, it is. Okay, so that's the swindle here. Because, of course, yeah. This is MH equals 125. MW is equal to 84 GeV. So no can do, as Harry was pointing out there, right? Yeah? That's. This is for a generic scalar, right, a heavy Higgs. But now, you see these plots. One of them's in my backup, which has the Higgs decay with the WW, and it's got for all the masses, including, 125 GeV, which doesn't work here. So what is actually shown in all those plots, but nobody ever bothers to tell you, is the fact that they're not H to WW, but what they are is H goes to W, goes to W star, and then this guy goes to F bar. Okay? So hidden in those plots is the fact that one of the W's is virtual decaying to the light fermions. And if you look at the plots, there's one in my backup of the decay for H to W pairs, you'll see there's a kink when you turn on that the second W can be real as a function of the mass. So yeah, this only works for heavy Higgses. So what you do here is you're going to integrate over the invariant energy of this W star, right? The Q squared of it to get FF bar, and you're going to use a narrow width approximation, which I'm going to work through in detail later how that works. So all those branching ratio plots for Higgs to W pairs are really this guy, okay? Not this guy, even though nobody ever says that. Yes. Okay, so a heavy Higgs if there had been, would have been very wide. And in fact, when you construct models where you have two Higgs doublets, for example, you might expect that you would get a wide Higgs. And typically you don't, because you get suppression factors, mixing angles, to make them. Yes? Yes. Yes, yes. Yes, yes. Very fine. Let me find a blackboard where I can write. Yeah, because the W, that other W is actually decaying too, right? Yep. So if you're really going to do this right and not be a slob, what you do is you calculate H goes to two W's. This guy was easy. Then F prime bar. And then this guy decays to F double prime, whatever, F, right? So the physical state has 4 fermions, which is what you actually have to calculate. There's a program called C4F, which is on HEP Forge, where you can just do it. But in point of fact, the narrow width approximation works pretty well there. So this is the right way to do it. But the narrow width approximation is numerically quite accurate because the width of the W is about 2 GeV. Okay? So it is indeed an example of a narrow width. But yeah, in principle, you got to calculate all these guys with the Ks and yes. Yes, this W, this guy. Yep. Yep. And that would not be contained in the narrow width approximation. And I'm telling you that that'll be smaller when you do it. But it is there. Exactly. It is there. But this dominates numerically. If the Higgs is allowed to be very heavy. Well, if the Higgs is allowed to be very heavy, what happens is that it almost always decays to 2 real W's. That's almost entirely. And the decays to tops are actually suppressed. And they're suppressed for a very interesting reason, which I'll probably get into later. They're suppressed because decays to gauge bosons go like beta, where decays to fermions go like beta cubed. So if you look in my backup to the branching ratios, you'll see that heavy Higgses don't actually decay very much to top quarks, even though you might have thought they would. They mostly decay to 2 real W's. Okay, anybody else? That's good. Okay. So.
It's only because of the beta cube that you have. I mean, I would have thought that the longitudinal enhancement is a big factor to get like momentum of W.
Well, the longitudinal enhancement is the big factor. It's MH cubed, right? It's MH cubed.
It wins over the top, right?
It's numerics. It's just numerics, right? It's MH cubed as opposed to MH. Its fermions are different than gauge bosons. The fermion decay width is MH. This is MH cubed if MH is big. And in fact, for the Higgs of 1.4 TeV, its width is equal to its mass. That's how it goes. Yeah. Yeah. Uh-huh. Yeah. Oh, good. You want me to work it out? Oh, good. I'll work it out. Yeah, no. Actually, I was going to work it out in my notes because it's fun. I like working out that kind of stuff. Because that's the whole point of this, is the longitudinal component of these gauge bosons, right? That's where all the action is. Okay. So I've got a Higgs decaying here to 2 W's. We'll call this one momentum P plus and this one momentum P minus. And this P plus is going to be E0, 0, P plus vector, say. Okay, so a longitudinal polarization tensor is where you just flip these guys. So epsilon L of P plus is equal to the magnitude of 0, 0, E over MW. Okay, so that's what a longitudinal polarization tensor is. But when I square P plus squared, it's MW squared, right? Because this is a physical W. So if you do some algebraic gymnastics, this thing is equal to P plus over MW, where this is the 4 vector. I'll put a mu here. Plus order MW squared over MH squared. Okay. So the polarization tensor is just the vector here, okay, P plus, for a longitudinal guy at high energy. So you can see what's going to happen now when I take the Higgs decays to 2 longitudinal guys. Okay, so let me get this right. The amplitude is going to be the vertex, IGMW, and then there's P plus dot P minus over MW squared. Okay, so it's just dotting in these 2 polarization tensors, so P plus, P minus over MW squared. Okay, so P 2P plus dot P minus plus order MW squared over MH squared. Okay, so for a heavy guy, the longitudinal amplitude is, what do I have? I G over MW MH squared. Okay, so that's where the MH to the 4th comes from in the longitudinal sector when I square that. So it's all the longitudinal guy. Okay. So in point of fact, you can actually measure the fraction of Higgs decays where there's a longitudinal W coming out, where there's a transverse W coming out. And the longitudinal guys are the interesting ones, and it roughly agrees with predictions. Did that answer your question? Good. Because later on I might do the same thing using Goldstone bosons, just to have some fun. Okay. Okay, so this is all very fine, but now you could say, well, what are we going to learn from this? Suppose I measured the decay width of the Higgs to 2 Ws to 4 fermions, or the decay or the branching ratio, say, of H goes to WW. What's that tell me? I mean, yeah, what's it tell me? How do I understand that theoretically? Okay. And that's where we get into the whole mess of electroweak symmetry breaking and effective field theories. Because in the simple-minded model I've constructed for you, there is no freedom to change the coupling of the Higgs to the W's. There's absolutely nothing I could have done with the particle content I had with one Higgs doublet to change this coupling. It's a prediction that the coupling of the Higgs to 2 W's is GMW. I can't change that unless I add more stuff, unless I add more doublets or something. So what the LHC experiments have done in the past run is they say, well, we need somehow to parameterize the deviation from the standard model. Okay? So what they're going to do, or what they did, is GMW W mu plus W mu minus H. Okay, that's a coupling I get in the standard model. And they're just going to parameterize it by a fudge factor, which we'll call kappa W. So in the standard model, kappa W would be 1. And they're going to measure the deviation of kappa from 1. And in point of fact, the latest numbers, which are in my backup, kappa W equals 1.00 plus 0.23 minus 0.20. So to about a 20% accuracy, they've measured this coupling as a standard model coupling. Okay, well, there's some problems with this. Okay, Anybody want to tell me the most obvious problem? Yeah, this is not a gauge invariant quantity, right? I can't do this. This isn't gauge invariant. Yeah? So that's very bad, breaking gauge invariant. Okay. And you can see where this might come in, because when I start adding stuff, well, let me draw a pretty picture. Let's see if I can draw a nice picture here. This is not the signal strength. This is kappa W as extracted from gluon fusion. So they fit these parameters. Yeah. No. And I'll tell you why. Get coffee break. No. It's close, though. Okay. So suppose...
Can I take a pause here? So this can be like gauge invariant when kappa W is 1, but you're worrying about the fact that this will violate gauge invariant only when kappa W is not equal.
So what's it mean to measure a deviation from 1?
Yeah, so that's the logic.
That's the logic. This is what the experiments have done in run 1.
Not that this term by itself is not gauge invariant, because once you add all other terms, it will be gauge invariant.
No, as kappa's 1. But so what's that mean? Kappa's 1 in the standard model. It's got to be 1. It's 1 in the standard model in my gauge invariant theory. So as soon as I let it be not 1, it's not gauge invariant. Well, and another way to say that is these aren't gauge SU2 cross U1 gauge invariant things, right? I mean, I can't just write down any old coupling I want for the W's in the Higgs. They have to come out of this SU2 cross U1 gauge invariant thing. Yeah. So now we're getting into where the wars are being fought at the LHC over how to do this. And boy, are there wars, right? Because this is pretty simple for the experimentalists. They measure these things. They measure branching ratios, then they pull these guys out. And then the theorists come in and say, well, gosh, guys, that doesn't make any sense. So let me just, yeah, nobody really wants to listen to us being brilliant here, right? I've had trouble with that in my life. Okay. H. Okay, so we can make the Higgs, say QQ bar goes to a virtual W, so I'll put a star on it, not to be a slob. And so here's my WW Higgs coupling, right? That's a nice thing, just using the couplings we have. And we'll let this Higgs go to two W's, remembering that they're really virtual W's decaying to fermions. Okay, so if I measure that, you say I can extract kappa W. But then I want to think more deeply, and I want to make this sensible. So what if I start putting in higher order corrections to this? I'm going to calculate this in my field theory. So I'll put in something like this, a Z, say. Oh, what a nasty diagram. But that thing doesn't factorize, does it? I mean, this is some complicated thing, but it's not WWH times a fudge factor. I don't know what it is, but electroweak corrections don't factorize like that. And you could draw lots of diagrams to show it. So what's a theorist to do? Well, the way to approach this and the way that the experiments are going to approach this whole question of verifying electroweak symmetry breaking at the next run is using effective field theories. Okay, so let's see here. Let me start. I'm going to kind of put effective field theories in everywhere I go for the next couple days. So effective field theory. You can ask an infinite number. I talk too fast. Yeah.
So in order to check the gauge invariance using the effective couplings here, I don't think it's enough to measure kappa W alone, but you have to measure all of them and then look at the ratios of that. And then if there is overall scaling factor coming out of the Lagrange, I suppose I can check that the effective theory is still gauge invariant. Because you change the kappa W by having loop correction, which does not involve this coupling but other things. So when the experiments fit this, they put a kappa for all the couplings, right? They put it, but it's still not gauge invariant. Yeah, but then I get it.
It's not. You put a kappa for all the couplings. This is just one coupling. Yes, thank you. Yes, it's not just W. You mess around with the Z coupling. So Z is written over there. Yeah. So put a kappa Z over there. Put a kappa. Well, I don't have any fermion couplings. Yeah, they put a fudge factor at every coupling they measure. None of them are gauge invariant. Sorry, none of them are gauge invariant. They're just fudge factors. So to do it better, or to do it in a gauge invariant way, we're going to use effective field theory. Yes! Yes, and that's what effective field theories are going to give me. Yes, absolutely. And the reason experimentalists don't like them is because they're very messy. They're not as easy as these fudge factors. But what can I say? Life is tough. So, my Lagrangian is going to be my standard model Lagrangian. And then I'm just going to start adding a bunch of operators. Sum over we'll call coefficients I don't know. Lambda I squared OI. This would be dimension 6 plus sum over, I don't know, K. I don't want K. Let's call it GI over lambda to the 4th. OI. Dimension 8. Okay. So, all right. So I can do this. That's fine. I just take my standard model Lagrangian. Then I start adding at dimension 6. I add all the operators that are invariant under SU2 cross U1. I just add them all. I write them all down, okay? And then there's some scale down here. So the first thing you notice is that they're only sensitive to ratios of couplings over scales. You don't get an absolute scale. They're couplings over scales. There are a lot of gauge invariant operators I can write down at dimension 6. If I forget about flavor, I get 59 just in one generation. If I put flavor in, I get 2,900 and something or other. Okay, so there are a lot of operators. But even just forgetting about flavor, you have 59 at dimension 6, of which 17 are CP violating. So maybe you'd be happy to assume CP violation, but there's still a lot of effective operators. Okay, so what are the rules of the game for doing this effective field theory? Well, gauge invariance, because that's where I started from the beginning. These effective operators only contain standard model particles, because if I discovered a new light particle, say, I don't know, 750 GeV resonance, something, new top quark, whatever, I wouldn't write an effective field theory, would I? I'd write a field theory with my new particle. So effective field theories are used in the scenario where I haven't found anything new. Okay, so there are no new particles here. And you just write down everything. Okay, so this effective field theory would be valid up to some scale lambda with some coupling upstairs. Okay, so here's where the wars come in. There isn't a unique way to do this. Okay, there are many different ways to do this. When I write down fermions, I'm free to use Fierz transformations to transform, one set of operators into another set of operators. Okay. I'm free to redefine my fields as I like. I'm using physical fields, so I'm free to use the equations of motion. That's fair. So there's no unique way to do this. Okay? In my backup, I have some of the operators in one particular basis. Some bases are more convenient than other bases for calculating higher order corrections and so forth. But there's no right and wrong. It's just convenience. But you have to write them all down to do this. Okay, so the standard model has all the standard model fields, where so far we've only really talked about gauge fields. Looks like this afternoon we'll talk about fermions. So somebody should have asked me, what about dimension 5 operators? Right? Why don't I have dimension 5 operators and dimension 7 operators here? Yeah. They violate lepton number, and I'll write them down later. So there are dimension 5 operators. In fact, there's one dimension 5 operator, but it violates lepton number, and I'll show you later on how that works. What time is coffee? Is it now? Okay, well, this is a good place to stop before I start writing down a bunch of operators here. Well, this is a good place to stop. Yeah, okay. So we'll continue this afternoon. Okay. Well, you should ask Tom if it's generic, if you have to clap after every lecture. I don't know what the rules are. Yeah. So we got our paper out. Awesome. Now you should write the next one. Hi, Laurie. How are you? Nice to see you here. Yeah.
I was wondering, so then what's the point not really one? I mean, is it
I don't see any point myself, but I mean,
because
a lot of people do, right? And it's just, I think it's just a choice for convenience, you know.
Okay.
Yeah, but I
It's
don't. No, I mean, no, right? It depends what you're calculating, right? It's like the gauge choices, or like the EFTs, which you know about EFT wars. Yeah.
and then you're saying, so they're trying to find a way to extract couplings that will gauge invariance, from what I've understood. But why not just looking at already like acyclic matrix elements, just like cross sections, and just giving the cross section so that?
Yeah. You know, there is a group in the LHC world that's trying to do that, but then it gets very complicated, right?
Okay.
There are these template methods where they're trying to define how you would do that, cross sections and distributions. This whole idea, where I'm going to go later, is putting in the EFTs, getting coefficients of the EFTs. It's to simplify it so that the experimentalists can do it.
But when you extract these coefficients from a process like that, then do you allow for deviations of the other couplings, for instance?
Yeah, they do global fits.
Okay,
They do
that's
global
great.
fits. Yeah, they do. Yeah.
Thank you.
Yeah. Yeah. Yes. Hi. Yes, I remember you from
Yeah, we
CTEC.
probably met before, but
Yeah, you were at CTEC last year, right?
Yeah, I was
Yeah.
at
I
CTEC.
remember. Yeah.
so for the effective field theory part, we both work on it, and I noticed that recently people are talking about these like relative importance of dimension 6, dimension 8.
Oh yeah, I'm going to talk about that this afternoon.
you're
Yeah.
gonna talk about it,
Right.
right.
Yeah. Right, because if you get a big effect from the dimension 6, then obviously you should have included the dimension 8.
Well, that's not necessarily the case because it really depends on like what UV theories.
Yeah. Right. And then you can't make these simple minded statements.
Yeah, so
Right.
I guess the question that I had in mind when I saw these Kappa framework versus effective field theory today was that if we include the higher dimensional operators, it might change the relations among the Kappas. Basically, what
Oh, absolutely, it
effective field
does.
theory
It tells you something about those
Yeah,
guys.
so-
But it also gives you new tensor structures.
Yeah, that's
It's not
true.
just rescaling.
Yeah, that's true. But as far as kappas are concerned, it looks to me like if we include, well, at least formally speaking, if we include higher dimensional operators and allow the cutoff to be anything, to be like not too much higher than the Electroweak scale. I mean, there are strongly coupled theories where we can do this.
Sure.
The kappas might just look like free parameters in some sense.
Right, it depends on your theory, right?
Yeah,
Because
depend on the theory.
right,
It
see,
depends
that's
on
the thing is you can't do it in a
interpretation.
model independent way.
Right.
Yeah. Because some of the
And then that would give you your
effective field theories, like CWW, for example, gives you a different kinematic structure than kappa
that's true.
W. Yeah.
There are other.
There are lots of examples like that. Yeah. So. Yeah. Okay. Good. Good.
Settling okay? Have you settled in okay?
All right. Yeah. Anything.
So, can you write a Yukawa coupling with just a triplet for the standard model quarks? How do you do it?
Just a triplet. Yeah. Why can't you do? What's the standard model quarks? Yeah.
no, but it would
And
be
then you-
left, and you, yeah.
So then what happens to the right? Does it have a bare mass?
Who cares? I mean,
You have a top quark or a bottom
well,
quark.
nobody's building phenomenological models with
Okay,
these.
but I'm
Yeah.
just wondering if...
Yeah, you
if
put an
it should have
epsilon
been-
in to get that to work out. Right. That's how you would do it. Right? Epsilon tensors. The right number, epsilon psi j.
You don't care about experimental. Okay, that's all.
Hey, man.
All right.
I'm just saying they don't work anyway, right? Yeah.
Right. So I was just confused about...
But no, but just we're talking a little differently. So he was like, I remember there were models where you had no doublet at all. I think, and you just had a triplet.
Yeah.
It works in different representations than what
Those were the 03 models way
Yes,
back
yes,
when. I'm betting that those old models didn't even give masses to
they didn't even-
the fermions. They were just worried about the W's and the
I see.
Z's. Yeah.
So they didn't worry about fermion representation.
This was a Glasgow
Yes.
way back in the time. Because the first paper with the fermion representations was Weinberg, where he put, this
Theory of
left.
leptons and
Yeah, that one.
fit together.
Yeah.
So I was also thinking you can't go any further, right? At least I guess there was a question: can you go to higher representations for the Higgs inside SU2? You can't because there are too many goldstones to be each.
Yeah.
3 is the max.
Yep. Yep.
Oh, that's interesting. I didn't think
Right.
about that.
You would have,
That's right.
yeah, you'd have too many goldstones. And you've got this goldstone boson equivalence theorem that says the longitudinal W's are really just the goldstones.
Well, you're just going to have massless particles.
If you have a doublet and some n-plet, then you're okay, right?
Doublet?
No, you have the doublet to get Let me move.
No.
But you still have to get.
Maybe with a Bev. Sure, with a small Bev.
It's got to be super small though, not to screw up the row parameter.
Yeah. But is it obvious that some weird like
No.
7, 10 plus 15?
No, the people who like neutrinos do that.
Oh, really?
Right, yeah.
What do they do? What do they do?
They put in triplets with super small VEVs to get super small neutrino masses. Yeah.
Yeah. That's
So they put in the Majoron and neutrino masses with triplets.
But is it possible that some like 25 plet will, by magic, like preserve the row parameter, for example? Like,
No.
is it obvious that?
Yeah, actually, Heather has in her lecture notes a proof that it's only doublets and
Oh, I see, I
singlets,
see,
and
okay.
it's really cute because it's from a spin analogy.
I see.
I mean, I've done it by brute force, where you put in the. Depends on the way you like to do stuff, right?
Did you say singlet?
What's that?
Doublets and singlets?
Yeah.
But singlet by itself can't help, right?
No, but it doesn't screw up the row parameter.
Okay, all right.
Yeah.
You always fine-tune things.
Oh, you mean the triplets?
Triplets and 25 plets.
You have to have the V prime be super duper small, right? There are limits that it's, I don't know, 10 to the minus 3 or something. You know? But, let me look at your name tag.
I'm
Hiya.
supposed to say hi from Tilman.
Ah, okay, good. You could tell Tillman I gave him a plug.
Yeah. I did, and he already said that it can't have been 20 years.
It was.
Possible. Yeah.
Yes, it was a while ago. Good.
Hi, I'm Yudai.
Hi, nice to meet you. Yeah. Yeah. No, I like when people have their name tags on. You guys should wear your name tags at the end. Too.
No, I wear these when I sleep. Like.
No, because the lecture, in the third week, they'll still want to know you. Right. So you're working for Kava?
Oh, I actually work in Mexico.
Okay.
But I also work for Startup. So I'm looking in
I'm Jeff.
Hi. And your last name is?
Drawer.
From where?
I think Cornell also. I'm an Ibar student.
Yeah, because I was doing mostly documentary thing, and now I'm starting with some collector
Yeah, I love that.
Yeah, I'm thinking of writing these up really well to have a modern.
Modern version.
Yeah, that's too old.
I mean, it's old, but I really like it. I feel like it teaches you quantum field theory from
I-
by trying to study the Higgs. You know,
I was trying to find something good about the EFT, though, written up, and I couldn't find anything. That's why I'm going to write this up.
So Dimension 7 also have a level.
Yeah, the odd ones all have left. And it's because the lepton doublet and the Higgs doublet have the same formula. So you can always make L5, right? So
But supposedly, yeah, if I so in principle,
Is your color just the light?
yeah, the lights are over here. Yeah, I see it. So if I hopefully want to
Well, I just wanted the one on the lower.
so you
I'll just leave that. I don't use it for it.
you're going to get a limit on the BEV.
One thing I forgot to mention.
Because it's going to contribute to the MW. And you don't want to contribute.
That's not working for
I know. And also, if you do want to use that for it, you can start with like the middle one. Doesn't. Yeah. Right. So like the front one here on that side will go up. Right. But the middle one will that one. If you want to use the chocolate.
Yeah, I will use triplets.
Well, I mean,
For my next lecture, I'm going to think about how I go across the board.
Did it not work out well?
No, that's fine.
Your handwriting looks bigger than mine. You're going to try to write bigger.
I bet if I wrote, I could write smaller and make it still see it. I'm just super sensitive.
Because usually they give you like a block. Sure, of course. No, but like these guys just give us. But that's what I think. I actually used it long ago. Because I didn't use it. I didn't use it. They gave us. Yeah. Like this. Really? Sure. Never seen that. Caramel, right? Probably. I still. No, like, run bed, like someone's eating a lollipop. I guess so. Really? That's the skill there. So basically, what? There's no so I think okay. No, I was not wrong. We met at a park. I don't want to explain the apparently it wasn't even a joke. It was not. That's why. Yeah. Priorities. What is a laptop? You do neutrino. Try it, man. Come back in 5 minutes. I'm really such a long This is really large. So, objective to describe
Schwartz. We have a big empty office over here where you can sit. Okay. Okay. So getting the key, and at some point you'll have to push papers. Okay, the key will do right now.
I mean, I don't. If it's complicated, I can go in any room. I mean, mostly I'll barely be hanging out here in the back.
Give him the key. It's not
I'm just worried
complicated.
I might lose the key.
Don't give him the key.
Now I'm
Why
too
don't you
nervous.
not give me the key?
No, okay.
Okay, if you
I
desire
think I'll.
it in
If
the
you
next
want it, you
couple
come back and
days.
ask it.
Yeah, I
Okay.
think I'll try. I'll ask someone to let me in.
Somebody else will have to
Are
be
you
in
supposed to give
there.
me lunch tickets or something?
Yes.
Yeah, how many
Go
would you
outside.
like?
Go outside and get them.
I don't know.
Go get them right now. We're not starting for 5 minutes.